everyone, in this video we are going to start talking about solving more exponential and logarithmic equations and their applications. And these problems are going to be a little bit more difficult as we go on than what we've seen so far, and they're going to allow us to use what we've talked about with logarithms, exponents, the natural log e, in order to solve these equations. So let's get started. Solve for x. Log of x plus 3 minus log of x equals 1. So in order to solve this equation, what we want to do is we want to write ourselves one exponential equation. Well, if you notice right here, on the left-hand side of our equation, right, we have two logarithms. Okay, there is a difference. Okay, those logarithms have the same base. So the first thing you should think to do is, oh, well, I can use my quotient properties of logarithms. And what that says is our logarithm has the same base. And remember, if we're subtracting, what we're really doing is taking the quotient of the two pieces of our logarithms. So this is equivalent to the log of x plus 3 over x is equal to 1. And now our log has a base of 10, so when we rewrite this as an exponential, we're given x plus 3 over x is equal to 10. And now we have an equation we can solve. Multiply by x, x plus 3 is equal to 10x. Subtract x, 3 is equal to 9x. Divide by 9, we get x is equal to 3/9, or x is equal to 1/3. So I can use my properties of logarithms to rewrite my equation as one exponential. Okay, this piece here, remember, it's really 10 to the first, which is just 10. So x is equal to 1/3. Okay, let's try again. Log base 5 of x plus log base 5 of x plus 4 is equal to 1. Well, now we're adding, okay, the sum of two logarithms with the same base. So that means it's the same as taking log base 5. Remember, we're talking about the same log with the same base, okay, of the product of x and x plus 4. So of x times x plus 4 is equal to 1. Well, what we need to do is we need to rewrite this equation as an exponential. So we have our x times x plus 4 is equal to 5 to the first, which is just 5. Distribute so we can solve for x. So we have x squared plus 4x equals 5. Well, notice this is a quadratic. That's going to end up being easily factorable. So in order to solve our quadratics, remember the first thing we need to do is set them equal to 0. So we're going to subtract 5x, x squared plus 4x minus 5 equals 0. Okay? And then we want two factors that are going to multiply to be a negative 5 and add to be a positive 4. So that's going to be a positive 5 and a negative 1. When we solve that equation, we see that x is equal to negative 5 and x is equal to 1. But remember, okay, what we're taking, okay, our logarithms of, those values have to be positive. So that means x equals 5 is not, negative 5 is not a solution. Your final solution is x equals 1. Make sure when you are solving, you do show both of them and clearly identify that x equals 1 is the solution. Make sure you also check that you can't take that value in your calculator. Okay? And you can always check, you can use your change of base, and it's going to come up with a non-real answer. Okay, so we're not using x equals negative 5. Now, what if we talk about the natural log? So we have the natural log of 3 plus the natural log of x minus 1 equals 0. Well, in this case, we're dealing with the natural log, so our base is still e, so we can still apply, in this case, our product property of logarithms, because the natural log is still a logarithm. So our logarithm keeps the same base. The natural log of the product of those two values, 3 times x minus 1, is equal to 0. Well, how do we undo the natural log? Well, we raise e to that power, or we write this as an exponential. So 3 times x minus 1 is equal to e to the 0th power. On the left-hand side, we can distribute. We have 3x minus 3 equals e to the 0. Well, what's e to the 0? 1. Okay, anything to the 0th power is 1. Add 3 to both sides. 3x equals 4. Divide x is equal to 4/3. We have those nice fractions. We can just leave them as a fraction. Okay, so remember, we're undoing each side. We're rewriting it as an exponential. So what our logarithmic property of equality says is a, b, and c be real numbers, such that log base b of a and log base c are real numbers, and b is not equal to 1. So if a equals c, then log base b of a equals log base b of c. We could also write this if our base is 10, log of a is equal to log of c, or if we want our base to be e, we can say the natural log of a is equal to the natural log of c. And we're going to use this property when our exponents do not have the same base, because what it's going to allow us to do is it's going to allow us to isolate that variable we are trying to solve for. So, solve for x. So 6 to the x is equal to 35. So here, okay, we have two values that are equal to each other. They don't have the same base. Well, what we want to do is we want to take the logarithm with the same base at both sides. In this case, for our first example, I'm going to choose base 10. I'm just going to choose my logarithm. So my common log. So I have log of 6 to the x is equal to log of 35. And this is what our logarithm property of equality is saying. If we have two values that are equal to each other, if we take the same base logarithm on both sides, our equation is still going to be equal. Well, notice on this left-hand side, I'm now taking the logarithm of an exponent of 6 to the x. Well, if you recall, okay, this is a situation, okay, for our power property. So log of 6 to the x is the same as taking that exponent and multiplying it by log of 6. So we have x times log of 6 is equal to log of 35. Okay? It's very important that you guys remember, okay, that log of 35 is a whole number. Log of 36 is a whole number. And by whole number, I mean it's a value that you have. So when you go to do this next step to isolate this x, this left-hand side is really x times log of 6. It's x times some number. It's not x times log times 6. It's x times log of 6. So in order to isolate this x, all we're going to do is divide. So you have x is log of 35 divided by log of 6. Okay, those logarithms don't magically cancel out and leave you with 35 over 6. That is not true. Okay, it's log of 35 over log of 36. They both are specific numerical values. Okay, so that is very important when you do this problem. Okay, the logarithm is giving you a value. So now we also do want to approximate to 4 decimal places, so we can go ahead, substitute this, plug it into our calculator. Log of 35 divided by log of 6, and we get this is about 1.9843. Okay. Make sure, okay, you do have the exact and the logarithmic value. Now, we can do the same thing with e. So remember our properties of the natural logarithm of e. So the natural log of e to the x equals x for any real number in x, and e to the ln of x equals x when x is greater than 0. And that's because the natural log and e, right, are inverses. They undo each other. They leave you with that x or that input value. So let's look at examples where we would use that. So solve for x. 2 times e to the 2x plus 1 is equal to 6. Well, we need to isolate that x. So what we need to do is isolate the e to the 2x plus 1. And since this is 2 times e to the 2x plus 1, the first thing we want to do is go ahead and divide both sides by 2. So that's going to leave us with e to the 2x plus 1 is equal to 3. Well, because our base here is e, okay, the easiest thing to do is going to be to take that natural logarithm of both sides. Because if we know we're taking the natural log of e raised to some power, it's going to leave us with whatever that power is. So our left-hand side here, the natural log of e to the 2x plus 1, because the natural log and e are inverses, it's going to leave us with that exponent of 2x plus 1 is equal to the natural log of 3. We applied our logarithmic property of equality, and we simplified. And now we just need to solve for x. So subtract 2x is equal to the natural log of 3 minus 1, divide by 2, x equals the natural log of 3 minus 1 over 2. That is your exact answer. Oftentimes, these are also going to ask you for approximations, so make sure you find the 4 decimal approximation. When you plug it into your calculator, make sure the natural log of 3 minus 1 is in parentheses because you are looking for that whole value. And divide that whole thing by 2, you get x is about 0.0493. Okay, so make sure you're given the exact and the approximate answer. Okay, so here we use the natural log because our base was e, so it's easiest to isolate the 2x plus 1 and isolate that x in the end. Okay, now solve for x. So 5 times the natural log of x, the natural log of x is equal to 7. Well, I have to isolate that x, so that means I have to isolate that natural log. Here, remember, it's 5 times the natural log of x, so the first thing you are going to do is divide by that 5. So the natural log of x is equal to 7/5. Please leave that as a fraction. Okay? And then we said, well, how did we undo the natural logarithm? Well, we need to raise both sides to an exponent with a base of e. So here, this is going to be e to the natural log of x is equal to e to the 7/5. And again, this is the same as our logarithmic property of equality. It works the same way with our base of e, just as if we were squaring both sides, right? You have to do the same operation at both sides. Well, now here on our left-hand side, e and ln of x are inverses, so that leaves us with just x is equal to e to the 7/5. And e to the 7/5 is your exact answer. You can go ahead and approximate. E is the second, if you hit the second button and then the division key, make sure when you raise it to 7/5, that 7/5 is in parentheses. It's about 4.055. Now, what if we put it into a word problem? So the problem size for a community of lemmings varies according to the relationship y equals y naught e to the 0.15t. Notice the resemblance to a equals p e to the rt. In this formula, t is time in months. Okay, y naught is the initial population at time 0. Estimate the population after 6 months if there were originally 5,000 lemmings. So this is talking about exponential growth. In case you're curious, some diseases work the same way, so maybe just take a look into that. So what we're going to do is we're going to substitute our values into our equation. So y equals y naught times e to the 0.15t. Well, our y naught is our initial population. What's our initial population? That's 5,000 lemmings. So we have initial 5,000. Okay. E is the base of our exponential, 0.15. T is the time in months. How many months? 6 months. We can go ahead and substitute this into our calculator. 0.15 times 6 is going to give us 0.9. So this is 5,000 times e to the 0.9. E to the 0.9 is 2.4596 roughly times 5,000 in your calculator gets you about 12,298 lemons. And make sure you do have a label as a word problem. you have any questions, please reach out and let me know.